So here we are going to revisit the previous example and look at evaluating this vector-valued function over the oriented curve C using an alternative parametric representation. So again, we are given the vector field, capital vector F, defined by the components 3x squared y squared, 2x cubed y minus 4. And C is the oriented curve running from the point 1, 2. So this again is our starting point to the point negative 1, 1. So this is where that curve ends. And it's important to make note of the start and finish so you can indicate the orientation of the curve. So let's start by sketching our curve C. So we have the ordered pair 1, 2. So that's where the curve starts. We'll put a little S here, our starting position. And this curve ends at the ordered pair, negative 1, 1. And that is where that curve ends. So connecting those 2 points with a smooth curve and indicating the orientation of our curve C, we can see that we have a line segment. So here, what I'm going to do to parameterize the curve C is to use a smooth curve. So C is a smooth curve, specifically a portion of a line. So let's keep in mind, of course, a line is defined as y is equal to mx plus b, and this is going to be such that x is greater than or equal to a, less than or equal to b. So we need to find this line. So let's start here by finding the slope of the line. So the rate of change of this line, we can say that this is 2 minus 1 all over 1 minus a minus 1, leaving us with 1/2. And now we'll use this and one of the points to find our y-intercept. So I'm going to use this starting point here as yx. So to find that y-intercept, we have 2 is equal to 1/2 times 1 plus that y-intercept b. So we can think about b as being equal to 2 minus 1/2, or 4/2 minus 1/2, which leaves us with 3/2. Beautiful! So we can say that therefore, the smooth curve for C is defined as this line, y is equal to 1/2 x plus 3/2. And now this is such that, and this is where you want to be careful. Right? We're starting at the point 1, 2. So the first x value is 1. And we end at the ordered pair, negative 1, 1. So this is how we're going to define the bounds. So we can say that x is greater than or equal to 1, your starting point, less than or equal to negative 1, the ending point. And so now we're ready to define that parametric representation for our curve C. So our parametric representation, again, using a smooth curve. Let's go ahead here and we'll let x be equal to t. And so therefore, y is going to be equal to f of t. And what I'm going to do, I notice up here, we've got a greatest common factor of 1/2 in that y coordinate. So I'm going to pull this out and say that's 1/2 multiplied by t plus 3. So we have parameterized x and y, and we can say that therefore the parametric representation, our vector-valued function r of t, with the components x of t, y of t, is going to be defined here now as t 1/2 t plus 3. And then don't forget your bounds. So this is such that t is greater than or equal to 1, less than or equal to negative 1. And again, those bounds are based on the curve's orientation, or what direction it's moving. Beautiful! So now we have our new parametric representation, and we're ready to go ahead and set up our vector line integral. So we need to parameterize that given vector field. So we need to now go ahead and find the parameterized vector fields. We're going to take those components we just found and plug them into our given vector field. So let's keep in mind, what were we given at the start? we were given the vector field, capital vector F, defined as 3x squared, y squared. Then we have 2x cubed y minus 4. So we are going to replace each one of these x's and y's with the parametric representation we found above. So the parameterized vector field will now be defined as 3 multiplied by t squared multiplied by 1/2 times t plus 3, and that's all squared. Then we have 2 multiplied by t cubed multiplied by 1/2 times t plus 3 minus 4. And so we can simplify. So we have, let's see, 3t squared multiplied by, so 1/2 squared gives us 1/4, and then squaring this binomial t plus 3, we're left with t squared plus 6t plus 9. And then moving on to the y coordinate, we see the 2's will cancel each other right out, leaving us with t cubed multiplied by t plus 3 minus 4. And let's take this one step further and simplify so we're ready for integration. I'm going to rewrite this x component as 3/4 t squared. And if you left it as it is, that's fine too. This is the same thing. It just looks a little nicer this way. And we'll take this and we'll distribute it through our trinomial. And we'll take the t cubed of our second term and distribute that through as well. So we are left with the parameterized vector field being defined here as 3/4 times t to the 4th plus 9 halves t cubed plus 27/4 t squared. And then our second term becomes t to the 4th plus 3t cubed minus 4. And we're one step closer to being ready to evaluate this vector line integral. The last thing that we need to do is find the tangent vector. And then we'll have all the components we need. So we want to find the tangent vector, r prime. So using the parametric representation of c we found above, we can see that our tangent vector, r prime, is going to leave us with 1/1/2. Oh, how cute. And we're ready to set up that integrand now. We want to take this tangent vector and dot it with the parameterized vector field. And let's give ourselves plenty of room. And here we go. Last but not least, we are again dotting the parameterized vector field with the tangent vector. So by the dot product, this is going to leave us with 1 multiplied by 3/4 t to the 4th plus 9 halves t cubed plus 27/4 t squared. And that'll be plus 1/2 multiplied by t to the 4th plus 3t cubed minus 4. Beautiful. And let's simplify. So we've got 3/4 t to the 4th plus 9 halves t cubed plus 27/4 t squared. And now we can go ahead and we'll distribute this 1/2 through to each term, which leaves us with plus 1/2 t to the 4th plus 3/2 t cubed minus 2. And we've got some like terms that we can combine here. We have 3/4 t to the 4th plus 1/2 t to the 4th. So we'll think about getting a common denominator here. So that's going to leave us with 5/4 t to the 4th. Let's see, what else do we have? We have 9 halves t cubed plus 3 halves t cubed. So 12 halves leaves us with plus 6t cubed. And then this will be plus 27 fourths t squared minus 2. And we're good to go. We've got the dot product here. This is that integrand. And we're ready to start evaluating our vector line integral. So here we go. Again, let's keep in mind that we were asked to evaluate the vector line integral over that oriented curve C. So we know this is equivalent to the integral from a to b of the dot product of the parameterized vector field dotted with the tangent vector dt. So again, just be careful of the bounds. We know that this oriented curve C starts at the point x equals or t equals 1 and ends at the point t equals negative 1. And we have the integrand 5 fourths t to the fourth plus 6t cubed plus 27 fourths t squared minus 2 dt. And look at this. All we need to do to integrate here is use the power rule. Lucky us. So this leaves us with 1/4 t to the fifth plus 3/2 t to the fourth plus 9/4 t cubed minus 2t. And again, evaluating from 1 to negative 1. So plugging minus 1 in, we are going to be left with negative 1/4 plus 3/2 minus 9/4 plus 2 minus, now we're evaluating at 1, so we'll have 1/4 plus 3/2 plus 9/4 minus 2. And let's combine up some like terms here. We got negative 1/4 minus 9/4. So minus 10/4 leaves us with minus 5/2 plus 3/2 plus 2. And very similarly with our second term, we can also combine 1/4 and 9/4 to give us 10/4 or 5/2 plus 3/2 minus 2. And we have even more simplification. We have minus 5/2 plus 3/2. So that's negative 2/2 or minus 1 plus 2 with our first term minus, so then we have 5/2 plus 3/2, so 8/2, which gives us 4 minus 2. So we have 1 minus 2, leaving us with a beautiful final answer of negative 1, which is the same answer that we found in the previous example, the same example, but using an alternative parametric representation. So this is a great example demonstrating to us that oftentimes multiple parametric representations for a curve exist. So it's up to you to decide what's going to be the easiest for me to integrate with. What do I see first?